We begin with Cholesky decomposition. For special case when matrix A is symmetric and positive definite, and it is very suitable for our structural engineering. In structural analysis, we have matrix K, stiffness matrix, that is symmetric and positive definite. If matrix A has the special property, now we can apply special numerical method. Now that is more efficient. Now we use less computational effort in low computational cost. And Thomas method for case that we have the banded matrix with a lot of zeros in coefficient matrix A. We're gonna go step by step, Gauss-Jordan. So we have three direct methods left: Cholesky decomposition, Thomas method, and Gauss-Jordan. And then I will talk about the computational cost, the number of operation actually of floating point operation, system condition, how round-off error influence your solution, how it's magnified the error in the input to the solution, the error in your solution because of round-off error. And at the end, I'm going to talk about the MATLAB backslash operator, which is actually employ what we learned. I'm going to cover that. Not sure if I can complete them all today. Let's see how it goes. Okay, we're gonna start with Cholesky decomposition. Cholesky is the name. Cholesky decomposition method. Or can be called Cholesky factorization, Cholesky decomposition. Today, 5th September. Okay. If matrix A, we consider A square matrix, n row and column, has the property of symmetric. The mathematical expression is that when A matrix A transpose equal to matrix A, it's called symmetric matrix. And the matrix A is positive definite. The mathematical expression is that when we pre-multiply a matrix A by vector C is the column vector, when we transpose become row vector, okay, and post multiply with vector C. We have A square matrix. We pre-multiply with row vector because that is column vector. Here we have scalar, right? The product here is n by 1, n by n, 1 by n. You end up at 1 by 1, which is scalar, and the product here is 0. Now for any non-zero vector C, that is member of real with n elements in space. Okay, for non-zero set, it's any non-zero vector C. Now, when the matrix A satisfy this, this product positive. This product is scalar, is positive. This is the mathematical expression of positive definite. But the way that we can check matrix A is positive definite or not. Now we will not try infinite number of vector C, right, and see how the product is positive or not. The way that we can easily check that our matrix A is positive definite or not is to check the eigenvalue of matrix A. So this is the first time that I mention eigenvalue. Okay, we're gonna make use of eigenvalue. Now this is very important concept in linear algebra. But let's say at this moment I'm not going into detail of eigenvalue. I'm gonna use MATLAB to find eigenvalue, and I'm gonna check that if all eigenvalues of matrix A is positive, my matrix A is positive definite. Not going to the detail of our proof for the eigenvalue right now. We can say that A is positive definite if all eigenvalue of matrix A are positive. So this is our condition. And you can have MATLAB help you. MATLAB has EIG function to return the eigenvalue. Okay. So if that is the case, now our linear system, the linear system AX equal to B, X and B are column vector. Now we can decompose into matrix A into a product of lower triangular matrix and upper triangular matrix. A can be, and we can prove that lower triangular matrix is the upper triangular matrix U transpose. I'm going to make use of this implication. Okay, I'm going to decompose so let's say that we perform decomposition. I'm going to tell you how we obtain U. Now, very simple. Now, by using the observation of the matrix multiplication. Once we have this decomposition, A decomposed into the matrix A, decomposed into U, transpose U. Now we can think of LU decomposition, right? Now we can think that I define this product as vector D. You start by solving for D using forward sum, and then solve for X using backward sum. So it's actually the same solver to solve triangular system, the same solution method. Now the different from LU decomposition is the way how you decompose matrix A. Okay, once you decompose matrix A, the solution process will be identical to LU decomposition. Now we have the two systems. U transpose D equal to B. This is the lower triangular system, and you solve for D. D will be unknown. And once we have D, D will be on the right hand side, and you solve ux, u, and the product of u and x equal to D. Now D is known. X will be unknown. The solution is backward sum. Okay, solution process same as LU, only different in the way how metric A is decomposed. Now let's start with there are two decomposition scheme that I will cover in the course. Now the first one is called the square root scheme. Square root, because our formula will be involved with the square root determination of the square root. The square root scheme A, we're going to decompose into a product of U transpose and U. We're going to make use of I will illustrate you the case of n by n equal to 3, the 3 by 3 matrix A. We have the matrix A 3 by 3. This is A11, A12, A13. Okay, A21, A22, A23, A3, and third rows, first column, A32, A33. U11. Now you can observe that the index of column is greater than the second index is larger than the first index. U2, U23, and U33. This is 0. All 0 below diagonal. All 0. And when you do the transpose, I'm writing here U11. This is actually at the second row, first column, but I know that its value will be U12, right? The same value, U13. And this is U22, U23, U33, and this is 0. And we make use of the metric multiplication. So this element will be from this and this, right? So it's going to be multiply U11 to U11 is a U11 square. I will go this quickly. U11, U12, and then U11, U13. Okay. It will be U11, U12, U11 square plus U22 square. Okay. U13, U12 plus U23, 22. Then the last set, U13 square plus U23 square plus U33 square. And then we match, equate the coefficient, equate the coefficient, equate the element, we can call the coefficient. And see that if we look at the first, start with the first column, you will get, start with this, you get U11. Remember, A is given. Metric A is given. So from this, now you get U11 is the square root of A11. Now you see the square root, right? The formula will include the square root. You get U11. And here means that A21 equal to U11, U12. And you have U11 known. So you can get U12. And for this, now when we move down, now you have A31 equal to U11, U13. U11 is known. And then you will get U13. So it means that you will get the first row of U. And then we proceed to the second column here. Again, we match the coefficient. Now A22, which is known, equal to U11 square plus U22 square. But we know U11, right? So we get U22 square. And then U31 is this one. Let me write here. Right? You will get U11, U12, and U13. And the first row of U. Here you get U22, and then U23. By matching the coefficient. And for this, sorry. Now we match A33 with the whole thing here. You get U33, and you can see that we have to now U33 equal to A33, subtract by these things, and then take square root. By this observation, now we can write the formula, and here's the formula. You may check. Now for general A, that is n by n. Now for A, n by n. For the general metric. Now not general metric, it has to be symmetric and positive definite. But general means that for n unknown, not just 3 unknowns. We can have the formula U, I. I means the diagonal. Now the diagonal element, the square root of AII, subtract by summation UKI square. Now K from 1 to I minus 1. This is in the lecture note. You can see this formula in the lecture note. And UIJ, you can see that, right? You can think that J is greater than I, because this is the upper triangular metric. We have AIJ, subtract by summation of UKI, UKJ, K from 1 to I minus 1, divided by UII, J equal to I plus 1 to N. Okay. And this is the formula that we will use for our coding. Okay, let's go to MATLAB, and we're gonna code, do the coding for Cholesky square root scheme. Okay, function, gonna create function. that return L U. Now we know that L is U transpose. So actually we are obtain U. Okay. And Cholesky 67D. Okay. And my input is matrix A. I put comment perform square root scheme. Of Cholesky for symmetric positive definite matrix A. SPD symmetric positive definite matrix A gonna return L lower triangular matrix lower triangle matrix, and L is actually transpose of U. U is upper triangular matrix that we will compute. Okay, Mn size A return one column that we expect to be equal, and then we initialize matrix U as a zero matrix. Zero. Now we use the MATLAB. Zero. N. Initialize matrix U. And then gonna start the for loop. Now I'm gonna put our formula now for I go to 1 to N. Now U I. Now our first formula is determination of the diagonal. UII go to square root. This is square root. And we have inside the bracket A I subtract by the summation. Then again, we're gonna represent the summation by the row vector multiply with the column vector. Our row vector is U from transpose multiply with U for I. Okay, this is U I, and then we have the for loop J, the second index I plus 1 up to N. U I J. Going to put it to the second formula A I J subtract by U K run from 1 to minus to I minus 1, right? This is K 1 I minus 1. This is our K. I with U I minus 1 J and divide by the diagonal I hope that I did it correctly. Okay, we have nested for loop. Now we have the inner for loop here for the off diagonal element and the outer for loop here. Now start with diagonal. We have to conclude that L for U prime. Because we have here two output, we have U. After the for loop, you get U, and you return L for the U transpose. Okay, I'm gonna save. Okay. Now let me consider the matrix. I'm gonna clear all variable. Okay, A. Okay, let's examine this matrix. So I check the eigenvalue. What I check, we can see that matrix A is symmetric. When you do the transpose, you can see that this the reflect the diagonal -6 here and here. When you do the transpose, the first column will be the first row. This is the symmetric matrix. So what we need additional check is the eigenvalue. Now we're gonna call the EIG. EIG return the eigenvalue. Actually, it can return also the eigenvector. But here we consider only the eigenvalue. So let's see. You can see that all eigenvalues are real, positive real. So matrix A is positive definite. Okay. And then we call our function. Okay. There's some typo. You line 11 UIJ AIJ U yes, thank you. This is AIJ, right? AIJ. And what else? Okay, should be okay. Let me run it again. Okay, I use semicolon here. It should be comma, right? Should be comma. Okay. Okay, should be comma. Add the semicolon. Okay. Okay. So what I get? L. Now this is L. L and U. L is, and we can check that L U is our original matrix A or not. Okay. And MATLAB has the built-in function show, and that will return perform Cholesky up show. And let's see if we call the built-in function, you get the same result or not. compare with our U. Same result. Now this is the square root scheme, right? The name comes from the formula that involves the calculation of square root, and we derive the formula from the observation of metric product, and we match the coefficient. That's the first scheme. Now we go back to the second scheme. Right? In the second scheme, we will not use the square root. Okay. The first scheme, square root scheme. Okay. The second, we call LDL transpose scheme. And we can decompose A into LDL transpose. Okay. We will consider the metric A. For illustration, I will use the 3x3 metric A. And remember that A is symmetric and positive definite. My metric A, A11, A12, A13, A21, 22, 23, 31, 32. Okay. So if I multiply matrix A by M1, that we think of LU decomposition, M1 the elementary elimination matrix that we gonna eliminate. When we multiply, pre-multiply A by M1, you want to eliminate this, right? In LU decomposition, this is actually the same M1. So what is my M1? Negative A21. Right? At this position, it's going to be negative A21 divided by the P1. It's going to be minus A21 over A11. And in this position, third row, first column is going to be minus A31 divided by A11. And matrix A will be changed if I multiply M1 to A. That will be A11, A12. And this will be 0. And A22 will be modified by row operation. Now this A22 is actually A22 subtract by this factor, multiply with this. Okay, so the prime indicate that value change at the 22 position. Okay, and A23 change. And here we have 0. That is our intention. We want to get 0 below the pivot, the diagonal. And this will be A32 prime, right? A33 prime. Now we make use of the LU decomposition. Okay. Now, okay. Then we start with pre-multiply A with matrix M1, and then I want to modify matrix A prime by post-multiply with M1 transpose. I'm going to define that this is my matrix A change. I post-multiply this matrix by M1 transpose. Transpose means that this column will be here. Okay. So actually M1A, M1 transpose. So I copy this. Okay, and then multiply with, and now the first column here will be the first row. 1 minus A 2 1 A 1 1 minus A is save space minus A 2 1 A 1 1 minus A 3 1 A 1 1. Now the blank means 0. Blank means 0. So what do we get? Here we have 0. 0. What do we get? Can write 0. Oh. Okay. So in this position, we have this multiplied. You get A11, right? And in this location, gonna be this and this, right? A11 multiply with this plus A12. This, and remember A12 is equal to A21. So this become 0. Interesting. Okay. This is 0 because we have you can do metric multiplication, and we know that A21 is equal to A12 because of symmetry. For this location, it's gonna be this and this, right? So this A11, I'm gonna show you this one, okay? A11 multiply with minus A31, A11, and plus 0 and plus A13, A31 equal to A13. So this is 0. So this become interesting. And this is 1, 1. This is, you can show that this is 0. I'm sorry, 0. This is A22 prime, A23 prime, So now this is from the M1 that pre-multiply, and this is from the M1 transpose that post-multiply. Okay, and we can show that this this matrix is also symmetric and positive definite. We can show that symmetric and positive definite. So now we complete the first step. The extension beyond LU is that now we want we post multiply. Now we post multiply with M1 transpose so that we get 0. Okay, in the second step, now we move to the second. Now we move to the second pivot. Okay, we What is our M2? We are now at the second column. I'm gonna fill in this, right? Now to eliminate this. This is my result after the first step. Now after first pivot, now we make 0 not only below the pivot, now, but also on the right of the pivot. Okay, now we move to this. This is our second pivot, our second diagonal, and we want to eliminate here, right? So what is my M2? Maybe negative A32 prime divided by A22 prime. Okay. And when we multiply to matrix A, this is my A prime, right? I'm sorry, A double prime, A double prime. So A will be triple prime. This is M2 A double prime. Will be now the second row same. Now first and second row same. This will be 0. Right? This is our intention. And we have the change at the A33. Change. And again, now we're gonna post multiply this matrix, by M2 transpose. Then A will be A4, will be A triple multiply with M2 transpose, and use multiply. It's M2 A M2 transpose. Let me copy this again. And then multiply with 1, 1, 1. And this matrix transpose. This will move to this minus A32 prime, A22 prime. Okay. And I can show that matrix A after post multiply with M2 transpose. Now we're gonna have this become 0. A11 0 0 A22 prime, and this will be 0. This will be 0 in the third row. Now we have A33 double prime, and we end up the. Let me change the color. We end up the diagonal matrix. At this step, we have the diagonal matrix D. Should have red here. Now this is 0 because we multiply this and this, right? A22 prime multiply with this, we get negative A32. Oops. Three. location. This location come from this. So I'm gonna write A22 prime. Okay, because of symmetry, this is 0. A32 prime, A32 equal to A23. Okay. So for easy understanding, we simply post multiply. We follow the process of LU, make 0 below the pivot. If you for this special matrix A, if you post multiply by M transpose, you're gonna make 0 on the right of in the same row of the pivot. Okay, and you end up the diagonal. So we can write that for this 3 by 3 matrix A, we can write that D is M2 and then M1A, M1 transpose, M2 transpose. One interesting property is that we have all here positive diagonal element. Now in linear algebra, the determinant is equal to the product of eigenvalues. If you have all eigenvalues positive, it means that you have the positive determinant. So here we have the positive diagonal elements, and we can write A, right? M1 by some manipulation, transpose M transpose. And this is my L. This is D. This is L transpose. L transpose scheme. The matrix L contain this matrix L store all multiplier, the ratio that we obtain by divide by pivot. That's called multiplier. Multiplier at each elimination step. Elimination step. So what is the advantage of LDL transpose scheme? The advantage we end up that solve one diagonal and two triangular system. By having A equal to from AX equal to B, have LDL transpose X equal to B. You may define this. Now you have L transpose X. Let's say that Y. I define Y. Okay, Y. Vector Y is vector C. Okay, this is vector C. So we first solve for vector C, right? Vector Z. We have LZ equal to B. So for Z, and then you have the dy equal to z. So for y, and L transpose x equal to y. L transpose is the upper triangular metric we solve for x, which is our objective. And here we apply the forward sum. Now solving the diagonal system is very simple. If you have metric D, let's say D1, D2, D3, the inverse of D is very simple. It's a reciprocal 1 over D. So simply divide right hand side by the diagonal element, you get the solution for this system, this diagonal system. Very simple. Divide right hand side vector by the diagonal element. Okay, and then you solve. This is backward sum. So now after decomposition, you end up solve 1 diagonal and 2 triangular system. Upper and lower triangular. Okay, this is number 1. Okay, let me number 1. And number 2. A half computational cost in terms of the number of operation, half computational cost of LU. Number 3, no pivoting is required. If A is symmetric and positive definite, no pivoting is required. Always stable. And in comparison with the square root scheme, no square root calculation, no square root calculation. Okay. Let's we have 15 minutes left. Let's do hand calculation for the a little bit big this example. Which example is it? It's gonna be the first example in the lecture note. The first example is illustrate in MATLAB, so I wouldn't call the first example. So this is the first one, the LDL scheme, LDL transpose scheme. Okay, given metric A 2, 4, minus 2, 2. Are we gonna do it together? Decompose. A 4 by 4. So it's a symmetric, right? Symmetric. Now let me check eigenvalue a little bit. Okay, eigenvalue are all positive. Now we have okay. Now the A is symmetric, positive, definite. Solution. Instead of if you recall the okay, thank you. Want to make sure that in Zoom we have okay, we have this in Zoom. Okay, we're gonna create L by this way. We have L start with identity matrix, and we're gonna fill in the first column of L. This is how we do. And L is the inverse of M. The first column is inverse of M1. Inverse is sign change. So what is the value here? This will be, it's actually this value, the element that we want to eliminate divided by the pivot. It's gonna be 2 minus 1, 1. Very simple. Actually, the element that we want to eliminate divided by the pivot. And we can find A prime. And the first row stays same. The second row means that we multiply the first row by -2 and then add to the second row. So we have 0. 0 because 4 minus 2 times, not 2 here. Now the factor on the multiplier, multiply this and subtract by 4. The 0, and then multiply 2, 8, subtract 9, we get 1. And -2 multiply to -4, subtract B will be positive. 4 subtract by 1 is 3. Okay. And 6 subtract by 2 is 4. I'm sorry, 6 subtract by 4 is 2. Okay. And similarly for the third row, we have 0, 3, 12, 15. And check this. 33. So we have 0. And I will know that if I multiply, now I don't have to do anything. I just make let me copy this. In the process, I will make 0 here. Without doing anything. Now when do I do MATLAB? Now remember that this is M1A, right? And this is M1A, M1 transpose. And this first column is M1 inverse, right? But I don't want you to, you can check with the mathematical formulation, but actually what we do, I'm going to show you how we do in practical way. You fill in column of L, the first column, second column, and what we do is the elimination. Now, once we get this, now we move to the second pivot. Let me copy my matrix L here. I'm gonna find M2, right? And what we do in our code is actually we're gonna fill in matrix L, second column. Now, what is my my value here? Now we move to the second pivot, second diagonal. What should be here? 3. We want to eliminate 3, right? Divide by the pivot. It's gonna be 3. So we fill in 3 here. And how about this? 2, right? And then we perform operation. Now we have 2, 0, 0, 0. And this becomes 3. Subtract by 3, multiply 1. It's a 0. And then 12, subtract by 3, multiply 3, subtract by 9. 12 subtract by 9 will be 3. And 15, subtract by 3, multiply 6. 16 minus 6. 9. Actually, we know that this is symmetry. Then we can get this matrix. Copy. Yes. And then I know that matrix A will be changed. Here will be 0. From the pre-multiplication. And with post-multiplication, we have this. In computer programming, we just make it 0. No real calculation. No real calculation. So what we left is the last step, the third step, because we have a 4 by 4. The third step yes. So you can fill in easily. This is 9 divided by 3. It's gonna be 3. So I get L. And this is my pivot. I want to eliminate 9. That's gonna be 9 divided by 3. The element that I want to eliminate. And here, 5th time change. Previous row does not change up to the 3rd row. So we're going to modify the 4th row. 9 subtract by 3. Now our multiplier multiply to the pivot. It's going to be 0. This is what we want. And 29 subtract by 27. gonna be 2, right? And the last step, this is the result that we make 0. And the last step we call A6. Gonna copy this and make 0 to the right of the third pivot and the last pivot. And this is my diagonal matrix. So we end up L D, L is here, LD, L transpose. Here's my matrix L. Now we can verify that A is L D, L transpose. And the process now is the extension of LU decomposition. Now we fill in L, and then we perform row operation. And from the property of symmetry, you know that at the end of the process, not only the element below the pivot, but element in the same row of the pivot will be 0. And at every step, you can see that at the end of every step, you will get the symmetric matrix. Okay, that's the, you can observe that. Okay, let me show you at the end of the process. Here, you can see that we have the symmetric matrix, right? 3, yeah, 2 here, 15 here. Let me highlight it. Symmetric. So actually, you can further save the computation, because when you do hand calculation, when you get here you get the second row, here you don't have to do the calculation, because you know that you can only compute the upper half of the matrix, upper triangular, because you know that it's symmetry. Here we have the symmetry again, right? Actually, you don't have to compute this value, because you know that it's gonna symmetry. Okay, now let me quote the LDL transpose. It's not a long quote, so new. Okay, function return L D LDL. Let me call LDL 67. We have the previous file, have B, and we have matrix A as the input. Now perform A L D transpose Cholesky composition. Okay, the LDL transpose scheme. Okay, where L is the unit lower triangular matrix that store our multiplier that used to eliminate coefficient below of matrix A below the pivot, and similar to the LU decomposition, and we have the D as the diagonal matrix. Okay, it starts with MN, but to find the size of matrix A, size of matrix A. You can add that if M is not equal to N, display the warning. L start with identity. I will create you the identity. Identity matrix. We're gonna fill in the column of L. The loop will be similar to the LU decomposition. We have the for loop from gonna use K for the column index. K from 1 to n minus 1. Okay. And then I have the inner for loop for row I. Now start from K plus 1. The row below the pivot to n. We have 4. We need to finish the for loop by ENDN. Okay, here inside. So if for every step, K, you can think of step or column. From first column to the column n minus 1. For the first column, you have diagonal at 1, 1 as the first pivot, right? For the and then we're gonna fill in L I K. You know that LKK is 1, right? LKK is 1. No need to do anything. So you're gonna fill in LIK with the elements that you want to eliminate. That is AIK at the position. Divide by A. You have seen this before. The pivot. KK. Right? And then we perform row operation. AI from column K below the pivot to the last column will be modified. I'm gonna copy this. Modify, subtract. You can see that we have subtract by LIK here. Multiply with the pivot row. The pivot row is A K. K colon N. Now here is the row vector. Row vector. Row vector. Take row K and column from column K to N. Okay. And this is actually LU, but in LDL transpose, don't forget that you will make 0 to the element on the right of the pivot. So what you do, A pivot is at row K, right? And then K plus 1 to N. You're gonna make 0. Right? And make 0 at the pivot row. Excluding the pivot element N. Okay, that is my code, and I have to assign D. Now L is also okay, because in the process you fill in L, and D is actually A. This is my code. This is the extension to LU decomposition. Because metric take advantage of symmetric metric A. Okay, let's check our code. Now we clear all, or simply clear CLC, clear screen, and I call A. Here's my metric. I can check eigenvalue of A again. Or shall we use the example in the we can use the in the iPad. Let me call clear again. CLC my matrix A. This one, right? This one, okay. I can check eigenvalue of A. All positive. Okay, all positive. And then I call this oh, I forgot to save the file. Save. Okay, here's my result. I have a semicolon here. Let me screen. Okay. Put semicolon. It is okay. Okay. So I want to see only L and D. Okay, here's my L. L is the unit, the lower triangular matrix with the element. Now this is the M1 inverse. This is M2 inverse. Okay. And so on, M3 inverse. Okay. You can verify that L, this is my diagonal matrix D. The L multiply D multiply L transpose will give you the original matrix A. Okay, here's the remarks on determinant and eigenvalue. Determinant and eigenvalue. Okay, that you should know. First, eigenvalue of lower triangular, upper triangular, and diagonal matrices are the diagonal entries or element of the matrix. And determinant is a product of diagonal element. Okay, this is the first remark that you should know. And all eigenvalues of symmetric matrix are real. And the third one is if matrix A is positive definite, and the determinant of A is greater than 0. So what does it mean? It means that you have non-singular system and you can find a unique solution. A determinant positive. It means that it's also, you can also call that metric A is invertible. It's invertible. Okay, that's all for today. We can show that the instructional analysis, our stiffness metric, is positive definite. Like we show the proof next week by the energy principle that you can easily verify that. Okay, that's all for today.